Welcome to this lesson on the Icebox method part 2. In this video, we're going to look at how to use the Icebox method when we're actually given the KEQ value to then go back and find our individual equilibrium concentrations for our products and reactants. So we're going to begin by actually looking at an example and working through this example using the steps from the previous video on the Icebox method part 1. So this example states that if 0.3 moles of SO3 and NO are placed in a 1 liter flask and allowed to react, what would be the equilibrium concentrations of each of the gases given that Kc, which is the same thing as KEQ, equals 0.5? So going back to our steps from the first video, first we need to rewrite our reaction, which in this case we don't need to do, we have plenty of space, and we need to draw our icebox. So I'm going to draw my vertical lines in between each of my components and then draw my horizontal lines to separate my 3 rows for my I, C, and E. Next, I'm going to fill in my icebox with everything that I know and everything that I've been given. So I've been given the amount of moles and the volume for each of my reactants. But because my KEQ is always in terms of concentration, I need to do my math and convert that into molarity. So for SO3, 0.3 moles over 1 liter is my volume in this case, so it makes my math really easy. So my 0.3 moles over 1 liter is going to be 0.3 molar for SO3. And NO has the same amount of moles as, NO has the same amount of moles as SO3, so 0.3 divided by 1. My concentration for NO is also 0.3 molar. And that's it. That is all I was given. I was given no equilibrium concentrations for any of my reactants or products. But I can still keep filling in my icebox with as much information as I can glean in as usual. So I know that if I have only reactants and they haven't given me any initial concentrations for my products, that I can assume that the reaction is going to proceed in the forward direction first. So my concentrations for my reactants, my products will be 0. And next, I can put in my x's for all of my elements or compounds and bring up any coefficients. But in this one, I don't have any coefficients, so all of my compounds just become x. Then I'm going to move those x's all down into my change row, into my C row, and I'm going to denote whether or not whether I'm reacting or forming each of these components by adding my negatives and my positives to my change row. So because I started with reactants, my reactants in my change row are all going to be negative because I'm going to subtract from their concentration to add to the concentration of my products. So since my products started with 0, I can only add to those. So they're going to have positive or plus signs in the change row. Now, since I don't have any numerical values in my equilibrium row, I can't actually solve for x. The only thing I can do is sort of plug things in so that I have algebraic equations and symbolisms in my equilibrium row. So for my SO3, I can just do 0.3 minus x. And the same for NO, 0.3 minus x. And NO2 and SO2 are just going to be x. So that's as far as I can go with my icebox for right now. But the question still wants us to find the equilibrium concentrations of each of the gases. But what they gave us for this example that they didn't give us in examples in the first video was they actually gave us the equilibrium constant, the Kc. So let's take a look at how we can use these equilibrium concentrations, even though I haven't solved for anything, and plug it into my KEQ equation to actually solve for x and therefore solve for those equilibrium concentrations. So since I know that Kc equals the concentration of my products at equilibrium over the concentration of my reactants at equilibrium, and I know that that's equal to the concentration of NO2 times the concentration of SO2 over the concentration of SO3 times the concentration of NO, I can actually just plug in what I have for my equilibrium concentrations. Even though there's still a lot of x's, I can still plug those into my equation since I know what my equilibrium constant is supposed to equal. So now let's clean some of this up and make this into a proper algebra problem. So I can start by simplifying it a little by making it x squared over 0.3 minus x squared equals 0.5. And then I can clean it up by taking the square root of both sides. So I get 0.707 equals x over 0.3 minus x. And then I'll multiply both sides by 0.3 minus x. Don't forget to distribute over on your right side of the equation. So I'm left with x equals 0.212 minus 0.707x. Add 0.707x to both sides to get 1.707x equals 0.212, and then simply solve for x. But looking back at our question, it doesn't ask us to simply solve for x. It asks us to solve for the equilibrium concentrations for each of our reactants and products. But now that we know x, we can simply plug it back in to our equilibrium concentration row and get our equilibrium concentrations for each of our reactants and products. So our equilibrium concentrations for SO3 is 0.176. For NO, it's also 0.176. And our equilibrium concentration for both of our products, NO2 and SO2, are both 0.124. And that's how you can use the icebox method when paired with the value for your equilibrium constant to find your equilibrium concentrations for all of your reactants and products. Bring any notes and questions you have with you to class.